Alright, so we have Unit 7, Lesson 2, and so we're talking about some specific ratios here that we're going to lead in to some more details a little later. And I think you're going to see a theme or a pattern here, but we're shown some triangles. We have a little triangle, then we'll have an intermediate triangle, then a little bit bigger intermediate triangle here, then we have a large triangle here. So I'm going to name this one like triangle blue. Get some blue ink going here. So triangle blue, right? And we have like a triangle, I guess purple here, which is blue, and this purple one here. And this biggest change here is going to be that the lengths are going to be additive, right? So the hypotenuse of purple is going to be blue plus this 2.5. Right, I don't know how well you can see that. So there we go, maybe that helps. So this is 5 plus 2.5, which is 7.5, right? And then we'll say that this next one here, and then this is, of course, this here is 6, right? This is 6. I think it's 4 and 2 is 6, so that's the purple triangle. Remember, that's still 3. And I'll shift to like orange to make it distinct. Alright, so this is orange, right, which consists of blue, purple, and orange. Right, so this is going to be 7.5 and 6.25. So this whole thing here, this whole thing is going to be 6.25 plus 7.5, that's going to be 13.75. And then this will be 6.5, or 6 plus 5, which is 11. So this will be 11 here. This will be 11. Alright, that's 11. And then finally we have the big long one, and we'll use burgundy, I guess. Burgundy is this whole thing, right? And then this little thing is going to be, this 13.75 plus 2.5 that's remaining. So this whole thing is 13.75 plus this little 2.5 that's left. So it's 16.25. So if we added up the segments here, 5 plus 2.5 plus 6.25 plus 2.5, 16.25, just a quick dummy check. And then down here, the entire length down here would be 11 plus 2, which is 13. And if you added all those up, just a quick dummy check, 4 plus 2 plus 5 plus 2 equals 13. Yep, so now we have the entire lengths of all these line segments, and if you don't recognize what postulate that is, that's the segment addition postulate. That's not that it matters for this, but just a reminder that that's a line segment addition postulate. But why does that matter for this one? Well, we're going to figure out, and we're going to look at the ratio of angle W here, and we're just going to call it angle theta, right, or angle W for the ratio of each one of these triangles, right? This one here was triangle blue. Triangle blue one, that's our small one. And GRW, that was our triangle purple. Triangle purple. And we had our intermediate one, which was triangle orange. And then we had our big one, which was triangle burgundy. All right, and I think you're going to see a pretty triangle burgundy there. Triangle burgundy. I think you're going to see a surprising theme here. Let me zoom out a little bit so we can see the whole picture here. All right, so there's the whole theme. We got all the numbers lined up, ready to go. So I'm going to do the opposite. This is our W, or our angle theta, right? And we're going to do the opposite value over the hypotenuse of each one of those. And we're going to do it for each. We're going to go right down the line and fill up this column. So starting with blue with our calculator. Okay, so our blue triangle, that's the little one. Our opposite is 3 divided by, and we're going to do it at 2 significant digits past our decimal. That's the hundredths place. So 3 divided by 5 is 0.60. Okay. Shifting to green, is it going to be 4.5 divided by, common mistake to think here would be 2.5. Don't make that mistake. The entire length of the hypotenuse is 7.25. That's why we added it up ahead of time, so we didn't make that mistake. All right, divided by 7.5. It's 0.60. Well, let's do the orange now. 8.25 divided by 13.75. I bet you can guess what it's going to be. Oh, wow. 0.60. Alright, and if we look at the last one, the burgundy one here, it's 9.75. 9.75 divided by entire length of the hypotenuse of this bigger one, 16.25. Bet you can guess it's, lo and behold, 0.60. So this means that the ratio of the opposite length over the hypotenuse length remains consistent as the triangle gets bigger, as long as the angle theta, or W, remains the same. Right? That is a pretty important concept to understand, because opposite over hypotenuse is a very specific ratio that we're going to get into next chapter, or next unit, next lesson. All right, now let's do the adjacent leg to the hypotenuse. All right, so the adjacent leg to the hypotenuse, so adjacent is this guy, and then this guy, and then this guy, and then this guy to the hypotenuse. And so the adjacent is 4/5, 4 over 5, to the nearest hundredth. 4 divided by 5 is 0.8. 0.08. That's wrong. 0.80. 0.80. That's the adjacent over the hypotenuse. Okay. And then if I were to figure out for the purple one, I bet you could guess what it's going to be. Right? So it's 6 over 7.5. Right? 6 divided by 7.5. Hey, look, it's 0.80. And then continue on with that same pattern using the orange one. It's 11 over 13.75. 11 divided by 13.75. It's 0.80. 0.80. And in fact, if you didn't get that value, 0.80, for the adjacent over the hypotenuse, you probably did the math wrong. 13 divided by 16.25 gives 0.80. That means that this length is 80% of this length. And that should make intuitive sense, because the hypotenuse is always going to be the longer length of the triangle. Alright, finally, we're going to be doing the opposite length over the adjacent length. And looking at this triangle, the opposite length, it seems to be shorter than the adjacent length. So you should expect a number to be less than or greater than 1. So if the opposite length is shorter than the adjacent length, you should suspect it to be less than 1 consistently. And if this trend continues and it is less than 1 consistently, and it expands, if both legs are expanding at the same rate, then the ratio should be consistent. Alright, so if you see 3 divided by 4, 3 divided by 4, opposite over adjacent, is 0.75. 3/4. If you have 3/4 out of $1, you have 75 cents. It's 0.75. Right, now we have 0.45. So the purple triangle, we have 0.45 divided by 6. 4.5 divided by 6. Decimal off. Again, we have 0.75. Right. Then we have for our orange, 8.25 divided by adjacent, which is 11, equals 0.75. Now, say for instance, I put it in wrong. Maybe I put in 13 divided by 9.75. I did it backwards. I'm like, wait a minute. That is obviously, I put it in backwards. Well, let me push this one over X. Oh, look, there's the answer. I put it in backwards. Oops. So I can still recognize that. 0.75. I put it in adjacent over opposite. There's the inverse of adjacent over opposite, 1/3, which is 4/3, right? If I put it over, that's 3/4. So once you start getting a hang of this stuff, you can start recognizing inverses and things like that. That's that handy button right there. Start seeing, they know, whoops, I reversed it. Okay, so there is that page. Move on to the next page here. Okay, let me adjust everything real quick. Okay. Oh, that's what I gave you guys. Oops. Yeah, so this should have been, yeah. So these are the for the decimal for the equivalent ratios. Yeah, so they are asking you for the fractions here. I gave you the decimal form. So you would just have the decimal forms in here. So that's all right. Again, rounded it to the so I'll give you in here, I'll give you the I'm not gonna do that for you guys, the table. Yeah, so when you're doing this in your homework, put these in as fraction form, and then when you're doing this, you'll just transcribe this in as decimals from page 1. Okay. So you'll enter this as fraction form in here, and then you'll just transcribe that as decimal form in here. Is what they want you to do. If you do it that way, that's fine. If you don't, and just do it the way that I did it, I'm okay with that too. It shows conceptual understanding. Okay. Alright, so we'll fill this out here. I'll do it in blue. The decimal equivalents of the blank ratios are equal. All three of them. Right, all three of them are equal. Okay. The decimal equivalents are equal. Right. I guess it does kind of show a point here. If they're different on here, it would identify that they're different, right? And then here it would transfer over to show that they are the same. I did it all in one step on this table here. I think the intent was met in both circumstances. Okay, that's because are they congruent or are they similar? Well, remember, in order for these to be congruent, right? Congruent means that the angles, the measures of the angles, and the blanks of the side are equal. Similar means that the measures of the angles are equal and the lengths are similar, right? So these are similar triangles, okay? Because the lengths are different. Okay, this is not true, right? So their sides are proportional. I guess this should be proportional. Okay, since these triangles share the angle and are right triangles, it is possible to define trigonometric ratios in any right triangle. Okay, so there you go. Go ahead and pause that and make sure that I didn't screw up anything obvious by checking the answer key. If I come back, that means that it makes any corrections. I'll make corrections. If I don't, that means there are no corrections to be made.